Lafleur's completion seminar, and thanks for coming. I want to recall first that we meet on Wurundjeri land, the land of the Wurundjeri people of the Kulin Nation, and I acknowledge their elders past and present. Dimitri joined us in, I just learned, 2013. I wasn't actually involved in the process right from the beginning. By the time I saw it, the thesis topic looked something like anything you ever wanted to know about unconventional gas but were afraid to ask, which perhaps looks a little daunting for a PhD project, but that wasn't quite enough. So Dimitri also chose to learn what we could see what we could learn about extraction-based accounting for fossil fuel emissions. And then, of course, it came time to focus on what we could actually learn in detail about this. And Dimitri will take you through some of the, let's say, character building aspects of going into the field to try and learn things in detail, and has put together, I think, a really interesting story of both the kinds of emissions that aren't necessarily obvious to us when we think about the sorts of accounting that we might do under old style Kyoto Protocol or Paris emissions. And around unconventional gas, this is a complicated story where the science is not necessarily very clear, and the science policy interface, as I've learned occasionally to my shock, attracts quite high level interest at the ministerial level in Australia. The occasional rather fraught conversation about coal seam gas. And it's really good to have some solid science trying to underpin and in some sense shake up this area, I think, where some of the assumptions we've made probably don't hold. And Dimitri's going to talk about this for the next little while. As usual, we'll probably go straight through the seminar unless there are questions of clarification, and then have a chance for some questions at the end. So Dimitri, it's all yours.
Thanks, Peter. Yeah, thank you for joining this seminar. I'd like to start off with thanking a few people. You've been seeing them scrolling past. I really would like to thank the college, the area that we are in. It's quite a special location, a special vibe that we have created here. And I think Malte should take quite a lot of credit for that. It's a very unique environment, and it certainly helped me completing this PhD. I also would like to thank my supervisors, Peter, Malte, and Mike. And in Peter in particular, it's quite extraordinary what he can do on a daily basis, and how much time he has set aside for his PhD students in general. So thank you for the time, the support, and the resources that you have put available to me. And I also would like to mention Ben, who is here in the audience. Ben was very instrumental in saving my fieldwork. And also the measurements that were necessary afterwards in the lab. So yeah, a lot of credit to him as well. So let's start off with an image from the planet and focusing on Australia. And I wanted to put this up there because it really shows you where the majority of Australia's fossil fuel exports are going. And it's mainly Southeast Asia and Japan. The emissions associated with this fossil fuel export are not really considered on a national basis. The emissions from combustions is not really our problem, it's their problem, whereas we are extracting them from our soil here. So Australia is the largest coal exporter in the world, and it's the second largest LNG exporter in the world. LNG becoming a real global commodity because it's compressed to liquid, which means that it's being able to be shipped around the globe. And LNG stands for liquefied natural gas. Natural gas is seen as a transition fuel by quite a few. Any forecast you see that comes up sees gas growing into the future. Other fossil fuels decline in their production, but gas is still seen as this bridging fuel from a coal-dominated world to a renewable-dominated world. So it's getting quite important. And the emissions associated with this gas on a territorial level are not very clear. We are very reliant on estimations. We don't really know what the emissions are. We sort of try to guesstimate what they are, and it is quite important because of the increasing growth in gas into the future. So this talk is split in 4 parts. One deals with the overseas emissions, so that's the extraction-based emissions. One deals with the emissions from unconventional gas. And then one part really tries to dive into the detail of how do you measure a certain type of methane emissions from coal seam gas in this case, because that's what Australia is producing. And I'll end up with some implications and conclusions. So let's start up with the extraction-based emissions. There's various ways you can account for emissions, and one of them, which is the dominant, is the territorial-based emissions. That's been used for the Paris Agreement, for a whole range of other studies. For example, the Brazilian proposal, which tried to calculate what the contribution is from nations to the increase in temperature. It's not necessarily attaching a responsibility to nations, but it tried to calculate what the contribution was. One PhD student from here, Jan Roubiot-Dupont, has done his study, which is also based on territorial-based emissions. And it just looks at what you emit on your soil, on your territory. Then on the left-hand side, another way of dealing with emissions is a consumption-based emissions. And then you look at what the emissions are from goods that you purchase in your country. So, for example, if you buy an iPhone, you live in the States and you buy an iPhone in the States, then the manufacturing emissions from that, consumer good are allocated to the United States. If the trade balance import-export is sort of the same, then you end up with a very small emission. So Australia, for example, in that accounting methodology has a very small emission because the import and export sort of cancel out. The one that I'm introducing here is an extraction-based emission. So what are the emissions associated with the fossil fuel production? And that really can inform the discourse on loss and damage and the responsibility for historical and present-day emissions in a different way. There's a lot of wealth build-up associated with producing fossil fuels, and the countries that are extracting benefit quite a lot of that extraction. So yeah, it can inform that discourse. I'm not going to run through the whole methodology. If you want to know all the steps, then please ask me during question times. I just want to highlight the only equation in this presentation, and that is how do you quantify the emissions of fossil fuel production? And that's really just looking at the production of that fossil fuel times a calorific value that is associated with the fossil fuel times an emission factor. And you acquire this data from various databases, and you run a Monte Carlo simulation to get the real range between the possibilities of the data that you have available. And then you sum up the extraction-based emissions with all the emissions from the country itself, which is land use, agricultural, industrial processes, using PrimeMap, which is the emission module developed at PIC. So here are some results. On the left-hand side, you see an historical overview of the emissions. On the top, it's the extraction-based emissions. On the bottom, it's the territorial-based emissions. And you can already see that it obviously has changed through time, but looking at the top figure on the right, there's quite a lot of different colors in the last 50 years. And that's really the spreading of the production of fossil fuel in various countries. And the one that stands out, say the last 20, 30 years, is this larger purple, let's see whether, so this larger purple area, the brown area, and the yellow area. You don't really see that in the territorial-based accounting, and that is Russia, Saudi Arabia, and Australia. And so those are 3 very big exporters of fossil fuel, which basically have a larger share in the global emissions at present day. On the right-hand side, you see an overview of a few countries. The blue lines represent the the extraction-based emissions. The red lines show you the territorial-based emissions. And you can see, for example, that for the US and China, those lines are fairly close together. So they are fairly self-sufficient in their fossil fuel use. Whereas the European Union is importing an awful lot of fossil fuel to sustain its economy. And Australia and Saudi Arabia, for example, are exporting a lot. If you then look at the comparison between the three methodologies, yeah, I have to apologize for the font. It's crisp, super crisp on the slides, and people who use Zoom will have a super crisp slide. It's just the resolution of the screen here who lets me down. So anyway, on the on the left-hand side, we'll see the split of the cumulative emissions since 1850 to now between the extraction-based emissions on the left and the territorial-based emissions on the right. And you already can see quite a lot of different shares of different countries. But it's more the one on the right that is interesting, which is the comparison between the extraction, territorial, and consumption-based emissions. Those last two have been used in the IPCC reports as ways of accounting emissions. But here you can see again that countries such as Russia in purple, Saudi Arabia in brown, and Australia have a much larger share in emissions. So Australia is responsible for, well, the contribution of Australia is around 3.2% of the global emissions, and that's been increasing ever since 2010. Another interesting aspect of this is if you compare the ratio of the extraction versus territorial-based emissions. So what is the footprint of countries compared to their territorial emissions? Again, the fossil fuel countries that export a lot of fossil fuels will stand out, so they will color red or purple. But there's quite a lot of African countries that have a similar pattern. And that shows you how complex this accounting is, because it's not necessary. Those are developing countries that are supplying the world with a lot of fossil fuel. Another one that stands out is Norway. Norway also has a very high footprint. I think it's 96% hydro for territorial energy production, whereas it exports quite a lot of fossil fuel. The wealth that is created by Norway is channeled back to the population by the Norwegian Wealth Fund, but that's surely not necessarily the case in, for example, the African countries. It's a similar pattern. So that was the cumulative pattern. This is the 2014 ratio. It's a very similar story. If you then look at the emissions per capita, what I just highlighted with Norway also comes out now. So on the left-hand side, you see the emissions per capita on the extraction-based emissions accounting, and on the right-hand side, you see it for the territorial-based emissions. And in light blue is what Norway has. So their extraction-based emissions are much higher than their territorial, highest of the OECD and the fourth largest in the world. Australia is not far behind. So Australia is, I think, around the 8th highest per capita. So the conclusions of this study really shows that the export, the fossil fuel exporters have a much larger footprint. If you would include those overseas emissions in their emission accounting, Australia is currently the 6th largest on the planet. And there's various African countries that have a much larger footprint. This really can inform the discourse responsibility of emissions, and it can inform the discussion on loss and damage and who should pay for climate change mitigation. It's been under review well, I don't think I'm not allowed to tell you which journal, but it's going well. And so then I'll want to shift gear to the fugitive emissions. And so going forward, gas is getting more important. So I really want to have a look at the emissions from gas. So is it possible that if you drill enough wells, that if you put a satellite on top of your country, can you actually see the methane emissions from gas? And so in the States, that's the case. In the United States, in 2014, there was a publication by Eric Kort, who showed that in the San Juan Basin, it's the biggest methane hotspot in the US, and you can see it from space, which is, I find, extraordinary. There are, in the US, they drilled 500,000 wells, oil and gas wells, in 2002 to 2014, so that's 12 years. And that's, yeah, it really shows the scale of what unconventional gas can do. So given there was so much data and research available from the US that suggested that the fugitive emissions were much higher, what do we know about the fugitive emissions in Australia from coal seam gas in particular? And so the Melbourne Energy Institute worked together with the Australia Institute, and we published 2 reports to really look at what we know and what we don't know about these fugitive emissions. And I've done a seminar on this, I think last year, so I'm not going to do that again. But it really ties into what Australia has promised in terms of their contribution to the Paris Agreement. It's an economy-wide scale reduction in emissions by 26 to 28% by 2030. And in parallel, we have this transition from coal to gas, which plays a big role in certainly the short term. Currently, the fugitive emissions account for around 7% of Australia's emissions, but that is reported. So it is based on the estimates that we think are there. It is not necessarily measured. And just to highlight how large gas emissions can be, this is a profile from North Dakota that shows you in the dark blue, refers to the y-axis on the right-hand side, that up to 35% of the gas is flared because there was just no infrastructure to do anything with the gas. In the unconventional boom in the US, initially it was all about oil. You know, that was what the oil companies were targeting, and they did not have any infrastructure to do anything with the gas, therefore it was flared. For the same reason, there are areas where you can't flare, but you have to vent, which is directly methane into the atmosphere. So the conclusions of those reports were that in Australia, we don't have any baselines. We don't know what the emissions were prior to coal seam gas starting up. There is quite a bit of, uncertainty of the emissions that are reported to the government and what Australia is reporting to the United Nations. The reported emissions are relying on emission factors. It's not based on measurements. There have been done a few measurements, but it's quite sparse. CSIRO is quoted here that reliable measurements on oil and gas production facilities, so other than wells, there's a whole range of other infrastructure that is available, are yet to be made, and that's still the case. And this is a report from 2 years ago. If you then end up underreporting your emissions, then it can have a real large impact on your emission inventory, because we're dealing here with methane, which is the second most important greenhouse gas, and a very potent one. The thing that is not part of the accounting is migratory emissions. And so this is very specific to coal seam gas. It's nothing, it's not something you should worry about if you're dealing with shale gas. But coal seam gas is something very different. You're trying to get gas out of coals, which are fairly shallow. And here you see a 3D cross-section of the geology in the Surat Basin. So that's the coal seam gas area. And what you see here, this white band is the target for coal seam gas industry, which are the balloon coal measures. And those black streaks are the coal seams themselves. They're not necessarily very continuous or thick, but they're there, and that's what the wells are targeting. The subsurface is littered with faults, and plenty of faults that are cross-cutting formations from below the balloon coals to above the balloon coals. And they can be conduits for methane if that is seen as an easier pathway than the wells. On top of the balloon coals, you've got the Springbok aquifer, which is a very good aquifer. So that contains a lot of water. And on top of that, you've got in this area, you've got this green narrow band, which is the transition layer. This is modeled. We don't know exactly whether that layer is there, but there is something that is sealing the formations below from above. From the sparse data that we have available, that thickness of that layer is quite thin in places. And that suggests that it's well possible that in between those data points, it's absent. And what that means is that you've got a very good aquifer in direct connection with a very good aquifer, which is this yellow-orange formation, which is the Connemine alluvium. And that is used extensively for agriculture in the area. And through that Connemine alluvium, you come the Connemine River. So what happens with coal seam gas development is that you try to get the gas out. That gas sits adsorbed on the coal cleats, and you extract an enormous amount of water to relieve the pressure from those coal seams that then gets the gas mobile, and you get the gas out via the wells. But that means that you're depressurizing the entire aquifer of the balloon coals. And so if there are pathways that are easier to access for that gas, if there are pathways, either faults or stratigraphic pathways, because formations are absent, then that gas is potentially mobile and reaches the atmosphere. So there are natural seeps in the area. There are natural seeps elsewhere in Australia, but we don't know anything about whether the presence of coal seam gas has enhanced these seeps. We don't know anything either what happens after coal seam gas, the industry stops and cease to exist. Those aquifers are still depressurized, and they take quite a long time to get back or close to the level that they were initially, which means that the gas remains mobile. And we don't know anything about whether that means that methane emissions will continue, or methane remains mobile and tries to seek pathways upwards towards the surface. So that really hinted, was for me a reason to go into the field and see what. Why is this not working? To see what you could measure. So the fieldwork really really wanted to measure what these migratory emissions could be and what sort of role the faults could play. And so I went into the Darling Downs region, and we tried to measure the atmospheric methane concentrations and the soil fluxes through the soil. And as you can see, it's agricultural land. There's hardly anyone living there except a few farmers. There's a few roads, and this is an area just south of Connemine, which is just south of the main coal seam gas belt. And that was the intention: stay away of the infrastructure, but not too far away to be really outside the area of influence. And so the most famous seep here is the Connemine River, which politicians thought it was smart to set it on fire. But so the Connemine River is a seep that has been increasing in activity. It also has decreased since 2016. We don't know why or why that exactly is. So the aims here were to measure atmospheric concentrations and soil flux measurements. And so the idea was, if you have that data available, then you can solve for the possible sources within that domain. And that includes agriculture emissions, because we are in agricultural land here. And the way you solve for these sources is with inverse modeling. This is the fieldwork area. And so what you see here is those red lines are the faults that are mapped from geological maps. So that those are present. And then the triangle is the triangle where we set up these monitoring towers to record methane concentrations from the atmosphere. And then the purple sections across those faults are the transects that we measured the soil fluxes. So there's quite a few on these faults, and then there were also a few that are away from the faults to understand what the soil is doing away from those faults. And yeah, so we set up our camp. Alex was there as well, and Steve isn't here, but he was there as well. And you know, it was all really relaxing, and we had some tools to measure soil fluxes, the soil temperature, and the moisture, etc. And this is how you link up the towers and the chambers to a Picaro, which is a spectrometer that can measure the concentrations, which you have to calibrate for reference gases and calibration gases. You obviously have to have electricity in the field, which you have to have inverters and generators and batteries, etc. And we also did some soil sampling to understand what the soil should do in the lab. If you would put it in a certain methane concentration, what does it do if it doesn't have any potential source from below? And so we had a few trials of ways of trying to contain the ambient air in a jar, in a temperature-controlled area. But eventually we ended up with a way of incubating the soil under different methane concentrations and analyzing it with a gas chromatograph. And so, yeah, really relaxing, fantastic. Great dinners, nice sunsets. It was great. It was extremely hard work. So, and this shows you why. Well, this is part of the reason why it was such hard work. This is one of the towers, which is P1. And that shows you that through the day, this is from 1 o'clock until 6 o'clock, you have these nice spikes. So you have indications that something is getting into this field domain carried by the wind, and shows you peaks of methane going through the domain, which was great. But then the other two stations really showed a very noisy signal. And that after we came back from the fieldwork, we understood that that was because the signal to noise ratio of those two spectrometers was way too high to be able to use it for inverse modeling. And that was a fault within those spectrometers, which meant we had one good set data and two sets of unusable data, which was was very unfortunate. One of the Picaros also broke down. We had 4 in total, and one broke down on minute 1 of the fieldwork, which meant that we had to do the tower measurements, the 3 tower measurements, and the flux measurements with 3 Picaros, and that became a logistical nightmare, which we ended up achieving, but it just meant very long days. So this is the results from the soil flux measurements. So here we're looking at a plot that shows you in blue the methane concentrations and in red the CO2 concentrations for a transect which is away from the faults. And if we zoom into this black area here, then you see that in between the green bands, which is the observation windows. So here you've got one observation window, and here another one, and here another one. So when this flux chamber is sitting on the soil, you see methane going down, and you see CO2 going up, which is exactly what soil on oxic conditions, so not submerged in water, should do. And so it takes up methane, and it should release CO2 during the day. If we then look at a transect on the faults themselves, if we can zoom in, then you see that at certain areas, you've got the methane going up, not everywhere. So the left and the right window, you see methane going up, and the CO2 also going up, which means that those locations in the chamber are emitting methane. And that's not what soil in general should do. If we then look at what the soil is doing in the lab under various methane concentrations in the incubation jar, then you see that under any methane concentration, the soil is taking up methane. And so the rate increases, but it takes up methane. And so, yeah, if you take the soil away from its natural environment, then it takes up methane. So if you then correct for the background that is there in the area, then you come up with quite a few locations that are emitting methane into the atmosphere. And if you then extrapolate this, oh, sorry, just one word on the, there's emissions in the area, and we also carried out some C13 measurements. So that's the isotopic composition of the methane that you have in your chamber. If we then zoom into the measurement window again, it's quite noisy, but this measurement can show you where this methane is coming from. And so the depletion in C13 highlights whether it's biogenic, for example, agricultural, thermogenic, which is the conventional fossil fuel imprint, or pyrogenic, which is the burning of biomass. And what you see here is that the red is the actual raw data. If you then average a bit out to get a bit smoother signal, you end up with anything between 50 and 52 roughly, which is on the borderline of being thermogenic, but there's quite a big biogenic imprint. And that is what the coal seam gas in the area is. It's very biogenic, but there is a thermogenic imprint from a later recharge from deeper down that adds this thermogenic signal to it. Given that the soil is so dry, we were there in the dry season, it is it's just not very likely that a biogenic source is the root origin here, and it's it really points towards the coal seam gas, the balloon coals, being the source here from the emissions. If you then scale up to the faults in the area, so what are the emissions from the faults in a larger area? You end up with yearly emissions of 34 to 190 tons of methane a year. And that is not very large. So in this small area, with just these two faults that we have here, they are not emitting that much methane. And it really shows you that you have to broaden this fieldwork to a much larger area, potentially closer to the fields, to get a better handle on whether other faults, I mean, we just had two faults, whether other faults in the area are emitting much more. So the fieldwork really showed that we can measure the atmospheric methane concentrations, which you can then use for inverse modeling. It shows that the soil is emitting methane at locations where the faults are present, that a purely biogenic source is unlikely, and it really calls for a real monitoring network to understand what the migratory and fugitive emissions are from coal seam gas in the area. So I'd like to finish with some implications of this work and other research pointers that I've been in touch with during this PhD. And the one that really stands out is this monitoring network. And 1/3 of Australia's gas is coming from coal seam gas, and it's only increasing. We still don't have any baseline. It doesn't mean that we can't do any baseline. We can still do it now and see what the progression of emissions are. It's not a static situation at all. And the combination of data that are available, so you've got the satellite data, you've got mobile data, you put a spectrometer on a car and you drive around to see what upwind and downwind of a field the emissions are. The collection of C13 is a key one, together with other isotopes to really narrow down where this gas is coming from. Measurements at wells and at facilities to understand what the emissions are at the infrastructure themselves. And together with subsurface data, there's a wealth of seismic data out there that shows you how the soil or how the subsurface looks like. And if that is available in a proper format, you can really interpret these faults and see where they're going and understand where you should be looking in your fieldwork. That data is not publicly available very easily. I think there should be, something should be done about that, because the seismic at the moment that is publicly available is pretty poor. We've seen that methane is seeping through the soil, and such a monitoring network is really an opportunity for agricultural and savanna burning as well, because they also will benefit from a more accurate inventory. It's really an opportunity to progress our understanding of migration and emission of methane, and what the impact of unconventional is on the planet's climate. So this C13 data is quite key, and there are other areas where this plays up. There's quite a lot of research in the last 2 years that has come out to understand what this decline in C13 is on a global scale. So this is the C13 data from the Cape Grim Observatory, and that shows you that since 2006 roughly, that has been going down. And people argue, well, because it's going down, that means that there should be more agricultural emissions, because that's more depleted in C13. Others said, well, no, fossil fuels have to have an impact, because the ethane concentrations in the atmosphere go up, so there must be something to do with fossil fuels. Others have suggested that the pyrogenic emissions are much lower than we thought they would be, which means that to get to the actual signal, we need to increase our agricultural and fossil fuel emissions. But there's no doubt that the C13 has been going down. So it is very different for different bands, latitudinal bands across the globe. So what you see here is 5 latitudinal bands from north to south, and you see that the stations that are color-coded per band have a different signal. So in the northern hemisphere, you've got a much more depleted methane than around the equator, and on the southern hemisphere. That might be due to different distributions of pyrogenic emissions, fossil fuel emissions, and agricultural emissions. But that's something that I think should be further researched. And if you then look at what has happened in the States, the sheer increase in unconventional oil and gas is just extraordinary, what has happened in the States. And if you look at the concentration rise of methane through the years since around 2006, which is the upper plot, and you compare that to when the actual increase of unconventional gas started, it's just a striking correlation. It's not a causal linkage, but it's just striking that it has happened when this boom in unconventional gas has started. If you then also look at what sort of coal seam gas, which is very biogenic in nature, has happened in the States, those 2 basins, there's 2 big basins in the States that produce coal seam gas, which is the Powder River Basin and the San Juan Basin, which are shown in black here, the dotted and the continuous black line. They sort of peaked around 2008, and that is caused by the move, or the ability to get shale gas out, which meant that at the start people were really focusing on coal seam gas, suddenly realized that it was just not economic anymore, and the shift was very quickly made to shale gas in the States, which meant that those companies in those basins very quickly moved. There are an awful lot of wells that are sitting there, orphaned, as you call them, which are not capped properly. Is it possible that they are leaking at a rate that they can influence the C13 imprint that you can see on a global scale? And we've done some calculations, and it's nowhere near enough to explain the whole shift. But the fact that you've got very biogenic methane in these basins could explain some part of it. So what you see here is a plot of the hydrogenic isotope versus the C13 isotope, and the Powder River basin. Oh, sorry. is very biogenic, which was all the coal seam gas. And there is another point here, which is the buccan, which relates to the image I showed you from the gas that was flared in North Dakota. That's also fairly biogenic. It's much more biogenic than you would think of a shale gas basin. And that sits roughly on the total isotopic composition of methane in the atmosphere, which is much lower than where you would expect the fossil fuels to sit in general. So it's a pointer, it's a question mark, but I thought it was quite interesting, and Mike with me. So Mike provided these graphs. Another pointer is that I think there should be more research done on the impact of low gas saturation and the stress field in Australia. Australia has quite a unique stress field, which is very different from the States, which is part of the reason why unconventional gas has not been replicated anywhere else than in the States. The idea that Northern Territory is potentially moving to shale gas, I think some research on what the effect of the stress fields could be on fracking is something that should be investigated. The other thing is low gas saturation. Obviously, every company is trying to drill for the sweet spots, which is fairly high in saturation. But the lower the saturation gets, the more water you have to get out, which means that the pressure is getting lower, which means that all gas that is sitting in this aquifer is getting more mobile. So it may well be that the emissions are going up because gas saturation is getting lower. And then, two things on the overseas emissions. So there is a real chance that the fugitive emissions in the developing countries could be much higher than you would expect, because not necessarily all the best practices will be replicated in those areas because of lacking regulation. And that's not just the developing countries. We've seen what happened in the States, much higher emissions. And there are talks around the possibility or the feasibility of shale gas in Northern Territory and WA. And this really ties into the remainder of the carbon budget that we have. The best estimates of the shale gas, shale oil, and the shale gas in the Northern Territory and WA are very, very large. So the technical recoverable in those areas basically means that it is possible to get those out. I know it's very remote, but coal seam gas was also remote, and that's now a very big industry. The CO2 emissions from the best estimates in the Northern Territory are around 0.6 to 1.5% of the remaining carbon budget for the 2-degree target. So for 1.5, that's even much higher. And for WA, Canning Basin is a very large gas basin. You end up to 3 to 4.5% of the total remaining carbon budget. It's work done by Climate Analytics, just came out 3 days ago. And so that really ties back to the transition. I mean, if gas is really part of the transition, then we have to talk about the transition. How long are you going to allow extraction and profitable business for an oil and gas industry? Because the emissions are potentially there for decades, and the infrastructure is there for decades, and that's where the industry is banking on. And then the last thing I'd like to just put out there is whether there's a case for climate change bystanders. So you've got fossil fuel suppliers like Australia, big fossil fuel exporters, and you've got countries that are demanding the fossil fuels, which are the consumers. And I think a neat analog here is the bystander smoking, where you've got people who are not smoking or producing cigarettes, but are affected and caused harm by the fact that there is smoke around. And is it possible that there are, at some point, when people are moving away from the negotiations on territorial-based emissions to understanding that harm is done, whether the small island states could argue that they are really impacted by the suppliers and consumers, whereas they don't have a real role to play there. And that really ties back to the overseas emissions here. That's where I wanted to leave it. The main conclusions is really that if you look at a different accounting methodology, then the fossil fuel exporters are contributing a much larger share of the total emissions to the planet, in the atmosphere, and that Australia is currently the 6th largest emitter. And from the unconventional work comes out that a monitoring network is really necessary. It's feasible, yeah, you really need to understand better what is happening in terms of the geology and the emissions and the impact of unconventional gas on the climate. So I thank you there, and I'll take questions. One, two.
Yeah, one more.
That's it. Oh. Any questions, Robin?
You say that monitoring. I don't need to sharpen. Great talk, thanks. You were saying that a monitoring network is feasible. Obviously, it's relatively easy to set one up, but the cost comes in the personnel that is required to oversee it, etc. Do you think there's a role, I guess, for policy or the industry to pay for that environmental impact? I guess it's an impact assessment.
Yeah, well, I think part of the solution here is that industry has to get on board, and I think it's well possible that they understand that something has to be done, and it's in their own interest to really understand what the emissions are. There are countless examples of where initially industry is reluctant to do baselines of whatever data that you can acquire, and finally afterwards realize that actually it's really beneficial and profitable to have that baseline information, because you can really pinpoint where the problems are. If you can conclude that emissions are coming from certain pockets, well, you address the pockets. So it's yeah, I think they should be yeah, part of the solution. And in terms of costs, I think the biggest cost is the spectrometers that have to be in place. And yeah, then there's a lot of things you can do with wireless and online. The stations that CSIRO has were fairly well equipped. So yeah, but yeah, I agree. Industry should be part of this this opportunity. Stan.
Does coal seam gas contain sulfur? And if it does, how does that compare with the sulfur content of shale gas and conventional gas? I mean, coal normally contains sulfur.
Yeah,
Sulfur.
I would say it would, because you're targeting directly the coal seams. But I haven't seen any research that suggests how much it would be and whether it's an issue. Because the thing that is getting mobile is the methane.
Yeah.
And I'm not sure how much gets with that to the surface.
Thank you.
Two questions. In that third bullet point there, there's, oh, sorry. Two questions. In that third bullet point there, there's a reference to the geological stress field. Can you explain what that, or define what you mean by that term? So basically, we're living on cratons on the planet. So there's the various cratons lying on the planets, and the Australian one is one of them. And every craton has a certain stress field. So the way the craton itself moves across the planet results in a certain stress field. So Australia is moving northwards, which means there is a compression element going on, which means there is the horizontal stress field is compressive. The fact that you've got an overburden sitting on top of, or basically below the surface, means that there is a compressional stress going down.
And so this is how the geological stress field basically determines under what sort of stress the craton is. So if you got a craton that is under extension, so basically splitting apart, then the horizontal stress field is extensive. So basically it moves outwards. Whereas if you got a compressional craton, basically moving into Indonesia, for example, which is happening with Australia, then the horizontal component is compressional. And the direction of these components is different than what is in the States the case. So it's much easier to drill wells in the States. It's much easier to frack them. Whereas in Australia, there are elements that change this stress field through the subsurface. So there are areas where it's much easier to frack a horizontal well, and there are areas where it's much easier to frack a vertical well. And if you don't know what's happening with that stress field in the area where you're targeting your fracking, then you can really end up with very poor fracking jobs. And yeah, it's quite possible that that's an issue in the Northern Territory because, for example, Thomas Flotman has published an article on what happens with the stress field in the Surat Basin, and it's not uniform. In the shallow part, I think it's easier to have horizontal wells fracked, and in a deeper part, it's vertical wells, or the opposite. I can't exactly remember, but yeah, that really has to be looked at, because if you're targeting a real big industry with a certain amount of wells, and you have to get tenfold of wells in there because you end up with vertical wells rather than horizontal wells, that means that your economical case is blown through the roof, plus the amount of emissions that are associated with tenfold of fracking are very large.
Thank you very much. That was a lot more detailed than I was anticipating, but I really appreciate. No, I really appreciate that, and I hope that other people do as well. Now, in the first bullet point, you mentioned the requirement for a monitoring network in relation to unconventional gas. What has been happening in definitional terms that I've noticed over the last few years, and first of all in the report that was produced by the South Australian Parliament at the end of 2016 into whether or not they'd let the industry into the southeast of South Australia, which includes the Otway Basin, effectively, and the major wine growing regions of the southeast, among other agricultural endeavours. And what emerged from that report was a conflating, if you like, of the definition of unconventional and conventional gas. So, and the introduction from what my reading anyway of the idea that you can actually frack during the process of extraction of conventional gas. Mm-hmm. So, given that that's happening, and so now it's becoming more common for wells to be regarded as conventional rather than unconventional, possibly to avoid any negative connotations. Do you think that it's appropriate to extend that point about the requirement of a monitoring network to conventional in addition to unconventional wells?
Yeah, I know which well
in the Australian context.
I know which well you're talking about. It is a very loose definition. Unconventional gas is just something that used to be not possible, and now it's possible for economical reason. Therefore, we're going to call it unconventional. It has to do something with the target. So shale gas is defined as unconventional. Very tight sands that there's nowhere you can get gas out without doing anything on the formation is also unconventional. Coal seam gas is also defined as unconventional because it's not the conventional reservoir, which is a carbonate or a sandstone, a nice porous sandstone. That specific case in South Australia, I've looked at the stratigraphy in the well, and in my view, the target that they were talking about is a conventional target. So the formation that they were targeting was a nice porous sandstone, and there's no argument that that's not conventional. Sorry? Sandstone. I think it was sandstone, yeah. They did target an exploration target deeper down, but they said they were not going to frack anything, and they didn't. So yeah, I think the argument there is more about, well, is it okay that funds from the government are used for unconventional exploration in a conventional well? And that's a very different conversation. But the actual target was a conventional target for the development.
But would you suggest that the conventional well would be worthy of the same level of monitoring?
Well, yeah, no, I don't, because the definition around unconventional is there is such a sheer amount of infrastructure involved, because you need thousands of wells, whereas with a conventional field you need, I mean, if you've got a really big field, then you need maybe 40 wells or something. But in general, a field can that are fields with one well, maybe in between 1 and 10. So there are not that many wells and that many infrastructure involved. And with unconventional gas, you've got so much more infrastructure, pipelines, compressor stations. Coal seam gas is very low pressure, which means every single well has to have a compressor. That's just a lot of emissions. And you don't, it's not such a different ball game for conventional gas. It's my view.
Interested in some thinking about what a monitoring network might look like. And this is inviting me to be speculative here. And even to think about what is it about the emission field that'll tell you what it looks like. So let me be a bit more specific there. You can imagine two kinds of emissions from a field. One of which is it's mostly broad scale, very smeared out emissions. It might come through the soil. It might come from lots and lots of small leaks and bits of leaks and compressors and all that stuff. And another one where it's hotspots. There's almost nothing going on most of the time, but something goes wrong. Every day something goes wrong somewhere else with engineering, and there's this venting event or something like that. Firstly, do you have any sense of what might be going on in the field? Which kind of monitoring, which kind of problem do we think we need to address? Both is kind of cheating. And then what does it mean for how we monitor, depending on what that emission field actually looks like?
Yeah, so there is quite a bit of data from the US that shows that the super emitters, these accidents or unrepaired wells, really skew the emission profile. So if you can target the super emitters, you deal with a lot of emissions from gas, oil and gas. I think they are fairly easily to be picked up. I mean, there's a real spike in methane emissions on that day, and you can very quickly target those super emitters. They may show up on drive-bys, or if it's a really big one. No, but probably not. But well, maybe not. Maybe you could see it on a time series of a satellite image if it's a huge one. But yeah, on a drive-by you could see it. You could have infrared cameras that try to copy the result from, for example, a monitoring network to see, do we see a super emitter in this area, because our inverse modeling shows you that it is. Yeah, I think if you can target those, you've got and they are present. If the super emitters are present and you can target those, then you solve a lot of emissions. But then there's all these other emissions that are present, and a network of multiple triangles can really target that. But I also think that you should have, for example, these chamber measurements. At this stage, I think it's fairly labor intensive, but you can do that if you know where you should be looking. You can target those faults as well.
The last question?
Yeah. I don't know.
Just a final point. There's a basin in the Northern Territory There's a basin in the Northern Territory. When you walk over parts of it, it just stinks of hydrocarbons. When you then look at the geology of it, it's riddled with minor faults and fractures. And along those minor faults and fractures are tar, seams of tar, little threads of tar. So the whole volatile content of the oil that was there has gone skywards and just left the tar.
Yeah.
And it's still bleeding a bit now. So that gives it an example of the problems you can have in highly faulted and fractured areas.
Yeah. Is that the Beetaloo Basin?
Pardon?
The Beetaloo Basin, or
no?
Ah, different one. Yeah. I mean that's, I would assume, natural, but yeah, it does show you what faults can do.
Thank you, Dimitri. Also from my side, fantastic completion seminar. I would have had a question if we had more time on what would be next PhD be on solving the mystery that Mike puts there forward.
Another one.
So no, it was fantastic. You probably heard as well the little plug from Dimitri, which was shamelessly orchestrated when he complained about the monitors or the projectors. They're actually sourced from IT, taken off the landfill site. They're recycled monitors from other lecture theaters here, which are too low resolution for those guys. If anybody of you feels like giving their students a hand so that they don't have to do these plugs in future completion seminars, we are happily inviting you for coffee. So thank you again, Dimitri. Great job. Yes. Yep. Do you have another future event to add?
I don't.
No. So we have two events next week. One 9:30 on Tuesday morning here. The Australian ambassador to Germany is coming, and you're warmly invited to attend and quiz the ambassador on all kinds of aspects of the Australian-German relations now that the German government has formed. So 9:30 next Tuesday morning here. That would be lovely if some of you are interested. Then on Wednesday at 11 o'clock, we have Cynthia Rosenzweig, who is a long-time veteran from the IPCC. We are currently close to be booked out for that event on Wednesday. So, but if you're interested, come along. And then on the, I think it's 9th of April, you find our the event details on our website. We have Simon Cobell here, the Victorian Renewable Energy Advocate. And although that is another lecture theatre co-hosted with Beyond Zero Emissions. So thank you so much for coming today. And again, thank you, Dimitri.